And the big seven starts where? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. It's the big seven on the periodic table. Okay, so zinc plus chlorine yields, this is what kind of synthesis? There's only two types. There's binary synthesis, and then there's the metal hydroxide synthesis, right? So, or the metal oxide. So this is definitely binary. So binary synthesis means that we have to make an ionic compound. Well, the ionic compound has a metal and a not metal. And what do we do with them? Crisscross charges. Okay, so zinc has a 2 charge, crisscross the 2 down here. So that's basically in my head or on your paper someplace, you're crisscrossing your Zn2 plus Cl1 minus to get ZnCl2. It looks like I just smushed it together, right? But we know that's not what happened. It's just what it looks like because we have the crisscross charges and it's balanced. And then might as well do this one now since I'm here. Zinc oxide plus water yields zinc hydroxide 2 because zinc has a 2 charge as well. And there is no 2 over here because what happened? They reduce to 1, right? So Zn2O2 crisscross down, drop your 2's to 1's because they're the same. Okay, so that's the first type. Decomposition. There are 4 types, so go back with me. We just talked about the 2 types of syntheses, right? Where we took 2 things and we smooshed them into 1. Big synthesis. What can we also do with those? Take them and decompose them, right? So this the binaries that we took 2 into 1, we can just reverse that and take the 1 back into 2. The metal hydroxide one, that zinc hydroxide, I can just take this guy and decompose it back into its original forms. So if you know your syntheses, you know 2 of the decomps. That's half the battle. And then you've got those other 2 decompositions. What do carbonates always break down into? Carbon dioxide, right? Carbonates is carbon dioxide. And what do chlorates always break down to? Friendly gases like oxygen, right? Not chlorine. Chlorine will kill us. Okay. So according to what I saw in some of y'all's papers, you need help on 4. Start with 4? Okay. So you guys can tell me the aluminum carbonate formula. Al 2 CO3 parentheses 3. Give me a thumbs up if you at least got that. Thank you, Jesus, because you have a formula sheet in front of you. You have your polyatomic ions in front of you. You should at least be able to access that if you can't do it in your head. Access your information and utilize that to give yourself some success here, okay? So carbonates break down to carbon dioxide. We know that's one of the that's the gas made, and this is heated, so there's a little triangle there. And I'm just going to try to stick with the same template. So here's our first example of a product made, and then what's left to still be combined over here? Don't just match up numbers, but it has to be aluminum what? Oxide, right? It's a metal oxide that is formed, and so it's aluminum oxide that's formed. So aluminum oxide is an ionic compound. So what do you have to do? Crisscross charges. Okay, so Al what? 2O3. So aluminum has a 3 charge, oxygen has a 2 charge, crisscross Al2O3. So what's not balanced right now? Then the number of oxygens and the carbons, right? How many carbons do I have over here? 3 for that carbon, because remember that backside subscript does distribute inside, so parentheses. And then carbon here needs a what? Do you add a subscript or do you add a coefficient? Yes, please do not add subscripts. Your formulas are perfect, right? You just work so hard to get your formulas. Don't screw them up. So now carbon has 3. Oxygen has 6 plus this one, 9. So we have 9 oxygens over here. How many do I have over here? Yay! And the aluminum's already balanced. If you're sitting there on that struggle bus and you're like, something is wrong, it's not balancing, it's not balancing, it's not balancing, stop trying to balance it. Go back and look at your formulas because something probably just didn't get crisscrossed. So don't let yourself spend 5 minutes on balancing because that's probably an issue with your formula. Another one on 1 through 5 on this section. Yeah. Number 5. Lithium hydroxide decomposes. Here's lithium hydroxide, right? 1 plus from lithium, 1 minus from hydroxide. You got that? Thumbs up. Okay, just seeing where we are. And then this is the opposite of the binary synthesis of a hydroxide. So what made that in synthesis? A metal oxide and water, right? Metal oxide and water. That's memorization. You got to keep turning that in your head. So I'll put water first just to change it up some. And then we're making a metal oxide. Well, what's the metal here? Lithium. So we're making lithium oxide. Formula? Li2, good. Lithium is a 1, oxygen is a 2, crisscross charges. You will literally crisscross charges every single time, at least once or twice throughout an equation. Today we're going to do it basically every time throughout an equation for every compound made. Oh, gotta balance this. There we go. Okay. How's that going for you guys now? The synthesis and decomp. Do you feel like, which of the 3 that we did yesterday, which is the most difficult? Synthesis, decomp, or combustion? Combustion? Is it because of the nomenclature? That organic? Or is it because you... Okay, hold on. I'm just going to give you the general theme. Most people love combustion because there's only 2 types. The first one is basically synthesis, right? It's basically... Hold on. My board is like freaking out on me right here. So, I'm going the wrong way. And combustion. Nope, I'm actually going the other wrong way now. Sorry, because I did this out of order yesterday. So, gotta figure out where I am here. I have an order, but I also like to change up my order too. So, with your combustion, you only have 2 types, right? This one's basically like synthesis, where you take your metal, singleton, you add it to a non-metal, you make a metal oxide, just like our first synthesis. So, if you know synthesis, you know combustion. Just the idea of combustion is one of the reactants has to be oxygen. That kind of really narrows things down for you, right? That's very helpful. And then the combustion of a hydrocarbon, again, hydrocarbons are hydrogens and carbons as a combined carbohydrate, basically. Carbon dioxide and water are formed. Do not put, don't just smush these together. Okay, it always makes carbon dioxide and water separately. So you should have those separately and then balance. Balancing, I can see where you might say there's a little bit more challenging. So tell me from your paper what some of the combustion ones you had that were of issues. I don't have a paper in front of me, so you guys don't have to tell me. Yeah. Can you tell me the formula?
The formula is actually no. I've the incorrect formula.
Can you give me number 5 anyway? Because I'm gonna do it.
Yeah, C3H6 is combustion.
Okay. Before I move from here, let's name this with our organic nomenclature that you have on your sheet from yesterday. So, if I have 3 carbons. What's my stem? What's my prefix? Pro. And you can see that there's a relationship between this and H's, so the 3 and then 6 H's. What's the formula that gets you from carbons to H's? 2N. Okay, so 2N is just 2 times 3, right? So 2 times 3 is 6, is where I'm getting that 6 from. So what's the ending of that? Ene, so propene. Versus propane. Propane, has everyone heard of propane? It's like propane tanks in your grills. Propane is C3H8. Propene is C3H6. Propyne, with the YNE, H4. So that change of H's is simply because of the single to double to triple bonds. That's what I was drawing on the board yesterday. Okay, so anyway, we know that's propene, and we're combusting it. So we're reacting with oxygen. What do all hydrocarbons always make when they combust? CO2 and H2O. Okay, so that's a standard, easy template to always just remember that hydrocarbons make. So now let's balance. What do you have to do first? Carbon first, so what do? 3 on carbon dioxide. Okay, so there's 3 carbons there, there's 3 carbons here now, and then I see 6 H's and I see 2, so I need another 3. Okay, so the 3's for the carbons and the 6 for the hydrogens have been taken care of. What's my total number of oxygens on this side now? So 3 times 2 is 6, plus 3 times 1 is, okay, so we see 9. And that's where we run into the issue. We did one like this yesterday. If it's an odd number of oxygens on the product side, and you've got an even number of oxygens on the reactant side, you can't really multiply those by a full number, right? So what would you have to multiply this one by to make it 9? You would have to multiply by 4.5 by 2, so 4.5 times 2 is 9. But we can't have half an oxygen molecule, so we go through and we do what to all of them? Right, because once we've got it balanced, it's balanced, right? So if you're going to keep it balanced, you have to increase everything by the same multiple. So this is now 2, this is now 9, 6, and 6. So that's a pretty good one to start with you guys. How about one of the first, I'll have it right here. been right in front of me the whole time. What if I said iron 3 is combusted? This is the one I want to see what you guys did. Iron 3 is combusted. What did you guys start off with? Loud and proud. Start for me. Fe what? Fe. So stop there for a moment for me. It's telling you iron 3 because iron's a transition metal, right? Well, when it forms an ionic compound in the end, you got to know the charge. Well, I'm telling you the charge up front, but that does not mean you write the charge. It's just there for your brain for later on crisscrossing. Iron, straight up iron, is reacted through combustion with oxygen, and what does it make? Fe2, I hear. O3, because what are you guys doing? Crisscrossing charges, right? So then, as you see iron 3 oxide forming, you gotta make sure that iron 3 and O2 minus get crisscrossed, and that's how you get the 2 and the 3 here. So balance it by doing what? Okay, I'm gonna hold off on that for a second. We're gonna keep that in our mind. Keep going. Then what would you do next?
Well, you'd have to multiply oxygen. You have to double it or whatever
Because you can't really get 2 and 3 to be the same, right? So what's it called when you multiply these by each other? Or the next number up? Least common multiple thing. So 2 and 3 need to go up to 6. So this will be a 3 here. Hi, give me 1 second. This will be a 2 here. And then how many irons do I have now? 4. So there'll be 4 there. Okay. Pause for just a minute. Thanks. That was easy. Okay. So in terms of synthesis, synthesis, decomp, and combustion, which one are you currently still like a little bit on the struggle bus with? You just haven't had enough practice to really know. Okay. Yeah.
I have a question. So for combustion, you said they don't add up. So then, like previously, you said if they don't add up, then you got your.
That means your formula was wrong.
Yeah.
Right.
So like, does it just depend on what you have to do?
No, like hopefully your formulas always are right? But if once you've written your formula and you're going through and you're balancing, you're trying to balance, you just can't get it to balance, it's probably because you've written something incorrectly. But like here, we really quickly saw we could balance it, so obviously we balanced it, so that gave me some extra like confidence, like, hey, my formula's right too, because it's balanced, I'm feeling good. But sometimes you're sitting there trying to balance it for 5 minutes, it's probably something's wrong to begin with. Okay, so do me a favor, guys. Let me scooch all the way back to where I was in the beginning. Here we are. I want you guys to do barium chlorate decomposes and calcium hydroxide decomposes. Do those two for me right now. Take just a minute. Write them on your paper. It's looking back at our notes, so it's really nice and it's very organized in your notebook and you can find things. I know. No, I see some people doing that because they need some help. Here. I see you guys looking at my periodic table on the wall. You know you have a best friend. I gave it to you the first day of school. You should use your periodic table because it's hard to see up there. Maybe your eyes are better than mine. Alright, Zach's table in the back. I can't see you, but I know you're there. Which one do you guys want to do? The top one or the bottom one? Barium or the calcium one? Zach's table. Top one, okay. So Zach, Riley, Annelle, and Gina, jump in when you're ready. BA. So barium chlorate. Hold up. We're not done with this. Barium has a 2 charge, chlorate has a 1 charge, crisscross. Okay, decomposes. I'm ready. What's next? Go for it, Annelle. Barium what? That's good to start with. Let me bounce away from barium for a moment. What do chlorates make when they decompose in terms of the gas made? Shh. O2, great job, guys. Okay, so there's oxygen being made. That's one of the products. So then fill in the gap. What does barium have left to bond with? Chlorine, right? So it's going to make barium chloride. What's barium chloride's formula? BaCl. No, 2. BaCl2. Alright, so BaCl2 is barium chloride. And then everybody up here now, what do I need to do to balance? 2 in front of oxygen? 3 in front of oxygen? Is that it? Done. Chlorine's already balanced. So that's 6 oxygens, 2 chlorines. 6 oxygens, 2 chlorines. We're good. Okay. Some of you guys really are eager to do this, so Shannon's table. Calcium hydroxide decomposes. We're on a timeline, so if someone could help me out here. OH. 2. Okay, calcium is a 2. Hydroxide is a 1. Decomposes. Uh-huh. Okay, so we know water is made. That's another product. Water is made. Calcium oxide is made, right? But that's a 2, and that's a 2, and that's what you were, I think, referring to when you said cancel out. Okay, calcium oxide, water, and it's balanced. Okay, great. So let's jump into, yeah? At it where? Oxygen is a 2 minus though. 2 plus 2 minus, crisscross, down, they both reduce to 1. Okay, so let's do ourselves a favor. Let's expose ourselves to the rest of the reactions out in the world. Minimally, but single replacement and double replacement. And I have some fun high school stories for you on this one. And I will use myself as an example. I'm going to be quiet for a moment to let you absorb and write down your general forms, which I think are very helpful. This is probably the heaviest slide for today. And we're going to do 4 examples of each one, and then we'll be able to be reaction masters. And if you guys need to shift around a little bit. Look. Types of reactions. Yep. So just jump in like that. And note that the first thing you actually look at first, you can We'll scroll down just a teeny bit here. Is that okay? All right, so we have now the 4 type reactions in that single replacement. And I think it's very evident that it's only a combination of a single element, so A, for example, here, and a compound. And that's just going to cause one switcheroo. In this case, who's switching? So A and B are just flip-flopping, right? A and B are switching. So here's my story for you, and then I'll talk about like the chemistry here. So dated this guy, 9th grade. He was a turd. His name was Chris. You know, he was nice. He liked science. He's a turd. There are other words I can describe you. However, so another guy was like, hey, so what we did this weekend? Comes into me, I does this thing. I was like, like, he's arm around me. It's serious, like in the hallway. I was like, I don't know what this is. He was in my English class, I used to know. So I'm trying not to turn right because this is kind of embarrassing. But I actually ended up marrying him, you know. He was my husband at this point. Yes. So, anyway. Okay, that's gotten embarrassing as you're looking at me. Okay. So, this is me. No. A, C. C is me. Me. Bonded to B, Chris. Not a cool guy. I was like, A's looking pretty nice. A's looking pretty nice. A's older, has a car. A likes science, likes me. Okay, let me just bounce out of this relationship, get with A. Okay, I got with A, and B was left out in the cold. Old boyfriend was left out in the cold. Yeah. So single replacement, right? You can think about any everyday life occurrence where that just kind of naturally occurs. However, in chemistry, we have to talk about like what two things could attract. I know it's the 21st century, and anything can attract anything else. But in chemistry, positives and negatives have to attract. So that's just how it works, because that's just how the attractions work. But in this case, B is a cation. A is a metal. So kind of just add these little annotate notes beneath here. And C is an anion. So I'm just putting metal plus minus. That's because it's a cation, anion from an ion, a compound. And then as you go farther, A, can you tell me possibly the charge of A according to how this is flowing here? A is going to be positive because cations are always first. C is the same C, right? So C in this case was a negative, so C in this case is a negative. And B is just left out in the cold as a metal. It's just a normal metal. It's not a charged particle. It's not ion. So just really helping you, like, do we write charges or do we not? And I'll represent this in a bigger picture in a second. Give me 1 second. So I can't just willy-nilly say I'm going to get out of this relationship, BC, and just go wherever. There has to be a method to the madness. So it's called the activity series, and the little tiny laminated sheet on your desk, pick it up. It has an activity series on it. On the back, it has the solubility rules. We're going to get to that in about 5 minutes. But the activity series is I'm going to call it the cuteness index. Okay? Cute things, really high on the top. Smart things, you can put any adjective there. Really high on the top. They're very active. If they are the single one like A is, it is going to get in a relationship. It is going to bond. It will. By all means, it will. So, in my case, husband was higher on the activity series. That current boyfriend, he was lower, so he got booted. So in this case, A was higher on the activity series than C. Nope, than B. Sorry, than B. I have to use my acronyms here. So A was higher on the activity series than B, which allowed for this replacement to occur. And if, sorry, there are some missing from the fact table, aren't there? Pass back a handful, Jacob. Thank you. So in this case, if something is not as high, then the reaction won't occur. That replacement would not occur. So I'm going to use like a real example with this in just a second. So that was cation to cation. You can also do anion to anion. What two things are switching here? C and A. So if A was a metal in this case, and remember metals form cations, then what is A in this case? Then it's a non-metal because non-metals replace non-metals here. So this is plus, minus again, yields plus, minus, and non-metal. Okay, so let's actually do a real life example of this. I'll take questions in just a second. So we have to talk about the activity series, and that's going to be pretty heavily emphasized here. Can I go forward? You know what? Before I go forward, I was going to do this with cards. Let's go. Tessa, Jacob, Kyle, you guys are on the front for a reason. You're going to be, hold up. You're going to be these people. Okay. Tessa, you can be pointing. Come on, guys. Come up here with me. Let's go. Read my examples. So, Tessa, you guys stand in the middle. All right. Jacob, stand here. All right, right here. So, sodium. So we have sodium and chlorine. They're bonded together, okay? This is the free copper. Ignore the charge because it doesn't have charge in this case. Look in your activity series and look at the two metals. What are the two metals in this example?
Copper.
Copper and sodium. Who's higher on the activity series? Sodium. Okay, so sodium wants to be in the bond. Is sodium in the bond? Yes. So sodium's in the bond, so this is never going to happen. There's no switcheroo, there's no single person. This is called a no reaction. Never would they trade. Start over. So you 2 points for you. Thank you for your participation. Let's see there. All right, so currently, what's the name of this compound? CuCl. Look at the charge. Copper 2 chloride, right? Because copper 2 is a charge. Sorry if I'm messing this up. So this is copper 2 chloride. Copper 2 chloride is a bonded. Sodium is the free one. Ignore the charge. Sodium being free, is sodium or copper higher in the activity series? Sodium's higher. So sodium's like, hey, I'm active. Switch to the side. So he got booted out in the cold. Sodium got back in the bond, right? Because sodium's active, copper is not. And thank you. You guys can drop your cards and see later. They'll take tips for their entertainment afterwards. Okay? Tips for their entertainment afterwards. All right, so let's do an example, and then I'm going to go back to the chart to give you some more indications. Write down your first reactants. First reactants should take you about 2 seconds. Calcium plus water. What are you guys writing? Ca plus H2O. Now, did I show you guys yesterday another way to write water? HOH. I'm going to show you just one other way, just to show you that there's an easier way to look at it. H2O is cool, but it's the same thing as me writing HOH like this. And I think it's actually very helpful to see the single replacement, because just like we saw the single replacement earlier, I have like B and C. Well, then we have water. It doesn't really look the same, but when you write it like this, you can definitely see the two entities of water. So, calcium, is it going to be able to form a positive charge or a negative charge? Positive charge, right? So it's able to form a positive charge. Who over here is able to form a positive charge? Hydrogen. This is the plus, this is the minus. So calcium and hydrogen are going to switch spots. They're single replacements. So when you switch them, who's left out in the cold? Hydrogen. But do we just write hydrogen like this?
Oh, no.
No, it's diatomic. You have to write it diatomically. And then calcium gets with who? What's OH together called? Hydroxide 2Y. Calcium's charge is 2. Awesome. Okay. And then to balance that, what would you need to do? 2 in front of the HOH. Okay. So this right here is the single replacement reaction, but it's not metal to metal. It's actually like on your chart. Do you see the little descriptors on your chart? It says replaces hydrogen from cold water. So everything here to this line here They're so active, they really, really, really want to bond. They actually boost the hydrogen out of water. They're that reactive. So these are very reactive. So you might need to add a note to your sheet that the ones at the top of the activity series are very, very, very reactive. Then down here, you can see it gets a little less reactive because it's only replacing hydrogen from steam, which is like gaseous water, and then from acids, and then so forth. So there's some descriptors on here that you might want to implement as you go. We're going to get to those halogens in just a second. So back here, zinc plus hydrochloric acid. Write down your information first. Write down your reactants. Thank you for bearing with me. I told you this is a lot of ammo today. Brady, what you got for me? Reactants. Sorry, hydrochloric acid. You're right, Cl's in there. Hydrochloric acid. H. It's actually HCl because the H has a 1 plus, Cl has a 1 minus, crisscross lines. I caught Brady because he was one of my good people with acids on the test. So, all right, so zinc and hydrochloric acid. Who would replace who? Zinc has the ability to form a plus charge, so does H. So then switch them, and what do you get? So who's left out in the cold? Hydrogen, like this, H2, and zinc. How do you write zinc chloride? Cl2, because the zinc drops the 2 down, chlorine is a 1, crisscross them. Crisscross, 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 and then you'll put a 2 here to balance. Okay? All right, so those are 2 different ones that didn't have a metal replacing a metal, but they followed the chart here. So zinc is here in the middle of the activity series. You can see that it can replace hydrogen from steam and anything below it, hydrogen from acids and so forth. So that's what we just did, replaces hydrogen from acids. All right, let's do the last one in single replacement. Bromine plus potassium iodide. Bromine plus potassium iodide. You're getting the language of chemistry here. So hopefully you can have them put down. Katie, help me out here. How would you write bromine? Sorry again? Br. Is it in the big 7? The big 7? Yes. Yes, it is. Okay. Who thought we should write bromine as diatomic? Because it's in the big 7. Okay, I'm going to point to the big 7 one more time. Where does the big 7 start? Nitrogen, N2, O2, F2, Cl2, Br2, I2, and then hydrogen. If it's in the big 7 and you're writing it by itself, you must write it diatomically. Okay, plus potassium iodide, Ki yields, this is 1 plus and 1 minus, that's why there's no subscripts. So in this case, bromine has the ability to form what? A negative charge because it's over closer to the nonmetals. So if it's forming a negative charge, it has to replace a similar thing, which would be who here? Iodine. So bromine and iodine replace each other. So then who gets kicked out to the cold? I2. Sorry, I didn't mean to tell you that. Iodine is diatomic, I2. And K gets with who? And how do you write their formula together? K, Br. It's K1 plus. Don't forget to look at your charges. Br 1 minus, crisscross, still 1s. Yes.
Okay, so the Br is
It's only diatomic when it's by itself. When it's in a compound, it gets to be bromine. Just bromine by itself, like normal self. All right. Good point. Yeah.
So why the bromine and the iodine switch instead of?
Because this is the ability to form an anion. Able to anion. And so it has to replace a similar one. And then it needs to be balanced. There you go. Okay. Yes. They're very unstable. They're very unstable by themselves, right? So bromine, so basically, bromine. As you can probably imagine, these are all very electronegative because they're up in the corner. Remember, up in the corner? So fluorine, chlorine, bromine, and iodine, they all have to just share one electron, and they're stable. They have octet. So they basically bond with each other, and they share one together, which gives an octet. So all of those on the halogens will do that very, very quickly, and they're gases, like they react very quickly. And then nitrogen and oxygen are very similar, except they share with each other 3, because nitrogen forms a triple bond. Do you remember drawing this with nitrogen? Yeah. And oxygen forms a double bond with itself. So they naturally react with each other, so that's how they exist in nature, is diatomic. Okay, good question. All right, so let's pause here for a moment. Look at the single replacements on your sheet of paper that we've been working from for the past day. I'm going to pause before I go to double replacements. Do 1 through 5. And you must utilize the activity series. If it's not active enough, it's called a no reaction. Not active, it's called a no reaction. This is what this right now. This is okay, sorry. Talk to people in your groups too. I wrote my 2 cents on the board if you are just trying to figure out, like, I know we just walked through these 4 times, but here's this, I think, the thoughts that you should have in your head as you go through. You write your reactants, you got those. Then you go, well, who could possibly switch here? Well, if there's 2 metals involved, the 2 metals are the ones you choose because they're both able to form cations. If there's 2 nonmetals involved, those are the ones that could switch because they're both able to form anions. But then, how do you make that choice of, like, do they switch or not? You have to look on the activity series, and if that one that's free, that cute one that's like, hey, like, I'm free, I'm single, that's the one you're looking at to see if it's higher. So the free one has to be higher on the activity series to make the reaction happen. So that's your thought process. Make sure you know that.
Fourth one, I don't think we don't need to know the critical composition. Yeah.
Oh, because it's like a no reaction.
Yeah, I don't think that's like normal water.
All right, take one more minute there because we still have double replacements. If you want to take a picture of this, take a picture of this. Yes.
If the water is hot, wouldn't that be combustion?
No. It just says it's basically telling you the water is warm, and there's some indicators on your sheet here. So like if it says replace hydrogen from cold water, only these metals are able to do that. These other ones can't. From steam or hot water would be this one. Steam is like hot water basically. It's not combustion though. That would require a lot of energy, like fire. Okay. Can I go ahead and go on to double replacements? You're at a stopping point here. Let me go over one maybe that you had an issue with on 1 through 5. 1 through 5, number 2. Josh, can you read that to me? Because I don't have, oh no, I do have it in front of me. I'm doing number 2. Aluminum is mixed. Aluminum is mixed with nickel 2-sulfate. Nickel 2-sulfate. Nickel has a 2-charge, sulfate has a 2-charge. Crisscross, crisscross, 2's drop down to 1s. So nickel 2-sulfate is NiSO4. And then what you'll notice is that this is a metal and this is a metal. Metals and metals can replace each other. Who should be higher on the activity series for this to actually react? Aluminum, the free one, right? The cutie over here, the single one. That's the one that should be higher on the activity series, is it? Yes, it is. It's higher than on nickel. So that does mean it will react. And so then aluminum gets with sulfate. And this is probably what some of you guys wrote. Shame, what'd you not do? Crisscross charges. Right, and that sounds half of my phone goes off, okay? And then nickel gets booted out to the cold. And that's your final, oh, sorry, not quite. You need a 3, and a 3, and a 2, and we're good. Okay, so double replacement's the last one for today. And so what I'm doing is really trying to give you baby pieces every day so that you see it every day. So your brain starts to realize, oh, this stuff's pretty important. I've seen it every day, and it starts to make connections again. So I can only do so much. I see you for 90 minutes a day. You see yourself for 24 hours a day. So you get the rest of this. Yes. That's a 3. It's a very bad 3. Sideways bird. These are like, you know, the birds. Like you draw like this. Like it's a bird. Sideways bird. Okay. Okay, my jokes have no longer sunk in. Okay, double replacement. Here's your set of instructions, and then we're going to go through this general rule stuff. And we're going to talk about solubility rules, which are on the back side. Thank you for bearing with me here. This is our last bit. We're going to practice with these. What's up, Mike? So this one's pretty easy. This is like, okay, so here's my fun story from high school. So you guys know I have a twin sister. It's our birthday today.
Oh, that's what
That's why there's a brand new little award. They were like, we're not blowing it up. I was like, okay. So we just take the blink report. So if I was, a tricky person, maybe a little mischievous, I would have me and my boyfriend, and then my sister have her and her boyfriend. See how this is going? Then we just want to play a trick on them. We do a double replacement. But the trick was that, did they know? Of course, I was way cooler. Like, her boyfriend didn't know. And I was like, I'm not Sammy, right? Like, oh yeah. So that was really early on. We gave them the benefit of the doubt. They figured it out. But that was basically a switcheroo. So, cation first, anion second. Cation first, guess what? Anion second, yet again. They're always going to be ionic. That means they always will have their charges crisscross. So, if this is me over here, who did I have to switch places with? I have to change places with X, which means I'm now combined with who? The other anion that's available. Because if I rebond with B, nothing happens, right? Because then X and Y can't really recombine. So that would be a no reaction. But in this case, A and Y do recombine, and X and B, because of their opposites in nature, do recombine as well. There we go. This one's pretty easy. Now, with this, we're going to use solubility rules. But let's just write the reactions first, and then we'll implement the solubility rules as we go. So, you ready, Freddies? So, you will be ready by the time I get there. Let me get to let's start with this one. Silver nitrate plus sodium chloride. And what I'll do is I'll give you guys like 2 minutes to get through a couple. Or I'll give you 5 minutes to get through a couple of these. Get it, we can go stretch break with this too. I know some of you guys are like, I'm sitting down for a while. Work with me here.
What's the word of silver?
Silver's number 1.
Oh,
Yeah? Like I will always keep doing that for you. Silver number 1. That way you don't forget. It's because I made it up, and that's the only way people remember silver's number 1. And in 5 years, you will remember me doing this. But if I just said silver's got a 1+ charge, you're like, I don't remember that. Right? I got it yearly one time, and I said, this is not for me. Oh my gosh, yes!
Only if you have chlorine by itself. I know this one. Got it.
Yes, that's it. because they all have 1 plus 1 minus charges. That's how it's going to work out like that. All of these have 1 plus 1 minuses. 1 plus 1 minus, right? 1 plus 1 minus. Because you know how to find them on the periodic table? Like a month ago you knew that, right? It's going to keep easy. All right, everybody, right now, write plus and minus under these as I am, so you have a sample example for yourself for later when you're like, what did we do in class today? Okay, so your silver is a plus charge, nitrate negative, sodium 1, chlorine negative. Who does silver have to bond with? So it makes AgCl, because this happens to be a plus 1 plus minus. This makes this very easy for crisscrossing charges. Who does sodium have to bond with? Nitrate, because that's the only thing left, right? And because it's an anion. So these two get together while these two got together. So in that case, that double date, double replacement kind of thing, we have formed 2 new products. But here's the deal. Well, there's all these like evidences of chemical changes that we know of. Shout out some of them. Bubbles, which is gas evolution, right? Say again? So oxidation, which is actually a formation of rust. What else? What else? So maybe a color change would indicate a chemical change has occurred. Making precipitate. So heat, energy, fire, things like that. So can you look up here and tell if any of those chemical changes happen? I don't know, right? Like you're looking at it, you're like, I have no idea if any chemical reactions or any chemical evidences are occurring, which means to you, maybe this reaction is like cool on paper, but it doesn't actually happen in real life. I can make puppy dogs and dinosaurs make puppy dinosaurs, but it means it's going to happen in real life. So what I've shown you is a theoretical reaction. Here's how we prove it occurs. You need to look at the solubility of these 2 products over here. So on the back of your activity series, which I've given you guys, on the back, I no longer clear this. Okay. On the back it says solubility rules. So what you're going to look at specifically, are the anions, and in this case, let me go ahead and tell you there are 2 categories of compounds. They're either soluble or insoluble. Which of these sounds like it's going to be a precipitate? Insoluble, not soluble, doesn't dissolve, right? So this one's going to be a precipitate down here, and these are going to be dissolved, meaning they form aqueous solutions. So if we identify something as soluble, we put AQ next to it. If we identify something as insoluble, we put PPT next to it to indicate it's a precipitate. So notice all of these are anions, right? What are the 2 anions in our example we just did? Nitrate and chloride. Okay, so here's what the rule is. All nitrates are soluble. None of those are exceptions. So if they're all soluble, what you'll do is put AQ over here next to nitrate. Put AQ next to nitrate to tell me that you looked at the solubility rules, you saw they were soluble. So now we're going to go back and look at chloride. Chloride, it says it's in the category of soluble, right? But then it's like, oh, but wait, there are exceptions. Compounds of silver, mercury, and lead are all exceptions to the solubility rules, meaning that they're not soluble, they're insoluble precipitates. So the ones you should always be suspicious of are those heavy metals, silver, mercury, and lead. So then under AgCl, we're going to put PPT for precipitate. Guess what, guys? This reaction occurs because we have an evidence of chemical change, right? That precipitate formed. You got me? Okay, let's do another one. You guys are finishing up these 2 down here. And this is like a baby solubility rules sheet. These like come in hundreds of rules, and we have like 10 here. So it's not all encompassing, but it's a pretty good start. So I'll help you guys with some of the other ones that don't have solubility rules. Keep going through here. Talk to your groupies. If you're waiting on me in the class, then work on the ones on your homework sheet. Don't waste your time. Yeah. No, unless it's like, okay, it's like this needs parentheses because if you put 32 on the end, like that 3 and 2 mesh together, right? So if it's like KOH, well, there's a 1 out here, right? So that, like, to me, doesn't matter because that 1's there. It's not messing up anything, but these definitely, because those are like absolutely necessary. Alright, so give me a thumbs up if you've looked on the board to check at least your outline of if your first reactants are right, and then you've done your double replacement correctly, and you crisscross your charges like a good person. Question? You have to crisscross charges if it's ionic. It doesn't matter if they're reactants or products. If it's ionic, you'll crisscross charges always. And I did up here too, but these were all 1s, so it doesn't look like I did, but I actually did. Katie? The other way, what do you mean by that? So like switched, that's no problem. But if you put FMG or NO, yeah, it doesn't matter their placement necessarily, but if they've got to be in the correct order in terms of cation first, cation second. Okay, now here we go. Back to solubility rules. What's nitrate's solubility rule overall? Everything's what? Is soluble. Soluble, right? So we put AQ here. And I did, is this balanced? Yeah, it's balanced. Okay, fluorine's not on the list. But that's really, really similar to who here? Chlorine, iodine, and bromine, right? So look at the rules for iodine, bromine, and chlorine. They're all soluble except for what? Silver, PB, lead, and mercury, right? So this is a suspicious character. And so what are you going to call this one most likely? PPT. Okay, so you can put, and I'm going to tell you, you might see me do PPT or you might see me do a down arrow. A down arrow just means it's a precipitate and it falls to the bottom of the test tube, which is what down arrow represents. So if I write that, don't fear, it's the same thing. Okay, lastly, cobalt 2 chlorate and calcium acetate yield cobalt, not just cobalt acetate, cobalt what? Cobalt 2 acetate. Let's use our terms, right? That's a 2, and that's a 2. And then calcium what? ClO3, 2. Okay, good. Don't say calcium 2 because that's not calcium. Okay, so these two down here, I don't know that the acetate, an acetate is on your rule set, right? What's acetate say? No exception, so they're all what? Aqueous. They're all soluble, so that's AQ. And then this one, chlorates is not on your list, but I'll tell you, and this is from another set of solubility rules, all chlorates are the same, aqueous. So guys, envision this. We have a liquid, and then we have this other liquid that we pour into a test tube. And then we get this liquid, and then this liquid. How cool is that? Not cool. Not cool at all. Did you see a reaction happen? No, there's no gas, there's no precipitate, there's no temperature change, there's no explosion. So this is a big no reaction. We just did all that work, and if there are no precipitates forming, you put NR to say no reaction, because it will look like nothing. Okay, let me stop for a moment, and I'm going to give you guys the last 20 minutes to do two things for me. Finish your little set of questions that are double replacement, which you have on your sheet, right? So the last 5. And I'm going to put up a set of instructions. I think I have it here. Yes, I do. I think it's this one. Might be lying to you. Okay, so basically, I have this car outside, and we're not going to put everything up today, but we're going to get a good start on it. You guys have your pieces of information in a PowerPoint or in a paper, which you've submitted to me. But the thing I need from you is, and I can make this bigger from the back, you're going to draw your molecule, put your name of plastic type, your car part that it's found in, and your names on just one piece of like neon color paper, which I have over here. That you need to break from chemistry, you think of this as stereochemistry. And we're going to be taping it to the car with like a piece of string or yarn to the appropriate location where it's found in the car. Okay? So I'm going to kind of leave that to you and also your reactions for the last 20 minutes of class. Okay? I'm going to leave the instructions up here. If you have a question, come and see me. And I'll show you more, but I want you gotta come see me in just a second. Yes.
Can you look at like my submission? I want to see.
Not right now, but I'll pull it up as soon as I stop this video.
Okay.
Was there a list on like a website that had like a list of classes so I can find?
Look under, yes, there is. It's under it's under the Google document. I can pull up that for you in just a second, okay? If you're